morning, everyone. I'm Iasonas from the call center Alpari, and this is joint work with George Papandreou, who could not make it today, so I'm standing in this case. So our entry in a nutshell is about exploiting invariance when doing classification and introducing this in deep convolutional nets. So we have two parts in this work. One is about having invariance to local transformations, so you can understand this as non-real deformations. And the second part of the talk is about global scaling and translation, and how to deal with it when training deep convolutional nets. So in a nutshell, our contribution consists in taking a standard max-pooled network, so this is our baseline. Using what we call the Epitomic deep network, we have reduction in the order of 1% in the error rate. And then using the search over global translation and scaling, we have a further decrease by 1.5%, and then just doing plain fusion, we practically go down to 10% in the error. And this is using the exact same architecture in terms of the number of parameters involved. Okay, so this is pretty much the story I will be saying here. To give a high-level overview of what I'll be talking about, this is showing the standard ImageNet. As you know, it's split in a convolutional and a fully connected part. And in the convolutional part is formed by a cascade of blocks which involve an alteration of convolution and max pooling. So this combination of convolution and max pooling can be understood as a translation-invariant similarity search. So what I'll be talking about here is first taking the blue blocks out and replacing it with another way of doing this deformation invariant template matching. And then in the second part, I'll talk about modifying the architecture so as to account for global scaling and translation during both training and testing. So starting with part one, namely modifying the individual blocks, I'll briefly talk about image epitomes, which are the starting point, and then say how we can use this thing in deep learning. So let's start with the standard patch-based modeling setting. So we have a corner-like structure. We want to represent it, let's say, with a dictionary for this structure, or this could be filters if we're talking about a deep net. So this would be distinct structures and would require separate filters to take care of them, even though we see that we have certain commonalities among them. So if we do not exploit these commonalities and treat them separately, what happens is that we require more data to train each of those guys separately, and we have also less power per parameter. Now, instead, what Epitomic propose is to pay a bit more and get a lot more out. Namely, we use a slightly larger patch, which has all of these structures included in it, and then we have a mechanism which crops a patch and also decides where to crop it from. So you can see and you can understand the epitome as a repertoire of patches. I should make it clear that we're not talking about using a larger filter. The size of the filter stays the same, but we have a data structure which allows us to couple the parameters of the distinct filters which are generated by the epitome. So this was introduced back in 2003 by Frey and Josik, and it has been extensively used in tasks like unsupervised learning of dictionaries for images, and typically in the generative setting. So its use in the discriminative setting was not thoroughly explored. So one step in this direction was in 2014 by George Papandreou and al. So what they showed here is that if we use the epitome to learn image representations in an unsupervised way, as an image coding sim, we get a much more diverse representation. So on the left we have an epitomic dictionary of mini-epitomes, and on the right we have the standard dictionary learning with the exact same number of parameters. So we see that we're comparing similar things. So still this result in gains in back-of-words classification on top of that. So this was for a flat classifier. Then the question is, now that we know that this could potentially be a better way of dealing with translation, how can we plug this into a deep architecture? How can we learn that? So for this thing, what was introduced by George in 2000 in a recent archive report is the notion of the epitomic convolution. So let's start with max pooling. So what we have in max pooling is that we have our dictionary elements, and then at a given image position, we search around it to find the closest matching image paths. And more concretely, we have k dictionary elements, and we're saying that the output at position I is obtained by maximizing over image positions the similarity of the filter with the local image observations. So now what we call the epitomic convolution is like a dual operation. So we're keeping the image position fixed, and then we're going into the epitome and searching for the most similar epitome paths. Namely, we have all of those candidate epitome positions which are compared to the image position here. Okay, so this is how we can write down the epitomic convolution. Now, in terms of functionality, we have the exact kind of mapping. We take an image out and we give an image in and we take an image out. So this can be now used as a module in a deep architecture. And practically what we're doing is that we're taking this convolution and max pooling cascade and substituting it with an epitomic convolution stage. Now, the parameters of the epitome obviously don't need to be trained generatively. We can use discriminative training. And in particular, it's straightforward to apply backpropagation to train a cascade of epitome layers. So what we gain by that is the most obvious thing is faster training because we have parameter sharing, so we don't train these distinct filters separately. So this is comparing training with max pooling versus training with epitomes. So we see that we have more reliable and faster convergence. And also in terms of test performance, comparing with a max pooled net, the error drops to 11.9%. So we have a 1% gain in error. I should note here that we're talking about the exact same complexity at test time and the exact same number of parameters. So we're comparing apples with apples. So this was it about dealing with the local transformation. Now, the second part of the talk is about dealing with global scaling and translation. So how can we deal with that when training a deep network? So I'll start with a brief introduction about scale, and we'll see that translation comes out naturally and for free. So let's say that we want to classify dogs. We have these training samples. Here the setup is that we have horizontally a scale-dependent feature and vertically a category-dependent feature. So let's say that this is detecting whether the image has ear-like structures. And now let's say that we have the task of distinguishing dogs from skyscrapers. That's the killer app, maybe. So this is showing the distribution for our features. And just to make the thing a bit more memorable, you can know that you have some ear-like structures on the rightmost skyscraper. So this is how your data would be distributed. And now, let's say that at training time, you just have a subset of this data, and you're asking to train a classifier with that. What you can learn is something entirely nonsensical, that large skyscrapers are supposed to have ears, while large dogs are not supposed to. We know that this is nonsense, because we know that scale has nothing to do with the classification. So the question is, how now can we make up for this problem? One thing that we can do is that we can modify our image, change its scale, and then accordingly change the resulting features. Okay? So as we upsample the left image and downsample the right one, we have our features having a trajectory in feature space. So practically, rather than having a single feature, we have a set of features coming out of it. And then we're saying that rather than having a single classifier score, we have a set of classifier scores. Now the question is, how do we exploit this insight to have a better detector? One thing that has been used in deep learning, so that was also last year by Howard and Al and also by Oxford Group this year, is to average these classifier scores. Okay, so you can say that maybe at one scale we failed, then at the other we're right, so if we average, we're doing something better. What we're advocating here is instead to say that we're using the max of those scores. Okay? So we're saying we don't really want the classifier to detect all tiny and all huge objects. We rather want to have a classifier who is demanding, who is focused on a single scale, and does his job right there. And then we will scale the image until it makes our classifier happy. So this thing that I'm describing intuitively amounts practically to doing multiple instance learning. We're training our network. So this goes back to 97 at least, and also earlier by Rumelhart and al. So what we're saying now is that rather than a single feature, we have a bag of features. What's nice here is that we can train this network in an end-to-end way, discriminatively. And what is also very convenient is that if we choose to use the max operation here, this fits hand in glove with max pooling. Now to see how this is super easy to do, we will have 3 steps. The first is something that was recently proposed by originally by Dubu and then by the Berkeley group in their dense network. The idea is that we have our image pyramid, and rather than extracting the features for each of those images separately, we construct a patchwork which contains all of those images together, so that's like a huge image that contains all of the different scale versions. And we pass this as input to our convolutional net. So this is a single GPU call. So you can understand that we have many small images in here and the associated features in there. So this was originally used as a computational trick to accelerate the extraction of convolutional features. But we're using this in a slightly different way here. The second step is that rather than having this convolutional fully connected split, we rather say let's do everything convolutional. So the last stages amount to trivial one-by-one convolution kernels. And now what our convolutional network will give us output will be the last neuron responses. These are the fully connected responses corresponding to this patch of the image. So now we're getting this for all of those distinct images that can be generated of the patch. And the very last stage is to do a global max pooling. Namely, we're considering all positions in the image, sliding our window in the patchwork, and doing max pooling in the output. So we have the classifier score obtained by maximizing over positions in the patchwork, which amounts practically to exhaustive search over translation and scale. And we also verify that if we add a spatially dependent bias, we have another gain in detection. So one thing is, as we said, that we're doing explicit position and scale search, both during training and testing, so we're consistent in how we're training our net. And what we get for free is localization. So we got our 48% localization error just by picking the argmax and regressing the position of the object. And this also is what gave us the largest boost in performance and the largest decrease in error. So we got 1.5% drop in error by doing this global search, and then by doing the fusion of the first and the second level, brought us back to 10.2. So that was our entry in a nutshell. Invariance in DCNN. We saw that we got systematic decrease in the error rate just by doing this simple things I was talking about, epitomic nets and global search. I should mention that this was using a 6+2 network, so this can be called shallow by now. What we know is deeper is better, so stay tuned. So we're working on it, and as soon as we have results, we'll put an archive report with all of those results together. So thank you for your attention. I would also like to thank NVIDIA for the hardware, CAFE for the software, the ImageNet organizers for the data and for assistance, and our organizations for supporting us. Thank you.
Time for a question.
And I'll be happy to talk at my first.